Welcome to the second part of the lecture on stoichiometric organometallics. Two questions arose from last lesson about the hard soft acid base concept. Well, at the end of the last lesson, we had this structure as a substrate, and this structure had this acylated pyridine, had three electrophilic centers, three Lewis acids. Therefore, this carbon as the hard electrophile. Here we had the soft electrophilic center, and symmetrically on the other side the same, of course, and there was an even softer electrophilic center in the para position. So the question arose was, why is this regarded to be softer than that? So let us compare it to an alpha beta unsaturated ketone. For alpha beta unsaturated ketones, we said that we have here with the carbonyl carbon the hard electrophile, and there we have the soft electrophilic center. Well, and if you compare that, well, let us form an iminium cation here, and then we have a similar situation. This here is the hard electrophilic center because the electrophilic heteroatom is directly bound to this position. This is more far away, so this is then harder compared to this one. And on the other hand, we have the same situation. Double bound electrophilic atom to this position. This is further away, therefore this is softer than that. And this is not called hard but soft, simply because it is in relation to this center, which is clearly the hardest one. Okay, that's it for the explanation here. So, second question. Well, there was this organocopper reagent. I've briefly shown and its reaction with cyclohexanone. I should explain here that this type of cuprate is a so-called Gilman reagent. This is a dimethyl. This is dimethyl. So lithium dimethyl cuprate. And in the reaction with the cyclohexene, I briefly mentioned that the copper preferentially coordinates to the double bond, preferentially compared to the oxygen. So, and we can assume that the lithium as the hard electrophile coordinates at the oxygen, and here we have the cuprate that coordinates to that double bond. By the way, the structure of the lithium dimethyl cuprate turned out to be an 8-membered ring system, at least in diethyl ether. with the two lithium cations coordinating. So let's start with a new chapter. It's about the synthesis of organometallic reagents. There is a rather nice general scheme that includes almost all ways how organometallic reagents are synthesized. And it's very, very simple. The best method available is a simple deprotonation. Well, okay, we have a base and we have a carbon-centered hydrogen, proton, and it is deprotonated if it is acidic enough. And if we use an organometallic base, butyllithium or, for instance, LDA, we could directly produce in this case, an organolithium compound. This is, of course, a methylation, this type of deprotonation. Okay? Very often, this CH group is not acidic enough, and if it's not acidic enough, and well, then we need to transform it first, well, for instance, into a halide. So this is generally the halogenation. And in most cases, this is then done in a radical process, a radical chain reaction. So, halogenation. From an halide, we can get to the organometallic species if we interchange the halide into the metal. So, this is a halogen metal exchange. You know this type of reaction very well from your undergraduate studies. The most famous example is the Grignard reaction. Okay. So, Grignard reaction works very well. You could also do that for producing organolithium, often also for producing organozinc, but with other metals it's far more difficult or doesn't work at all. In that case, you first lithiate or form the Grignard reagent or the organozinc reagent, and then you transform it into the organometallic species you had in mind. So here you have to exchange the metal, and this step then is called a transmetallation reaction. So, deprotonation, well, as I said, you could use, for instance, LDA or butyllithium N-butylithium, secondary butylithium, or even tertiary butylithium, or sometimes potassium T-butoxide. We don't need to comment on the halogenation. Well, later on I will comment on these steps. Just a question, do you know even more reactions, methylation reactions, which do not fit into this general scheme? At least one you should know. Very simple. The hydroboration. Hydroboration doesn't fit into this. So, what about hydroboration? Well, okay. As a general scheme in this case, let's take a metal hydride and an olefin. In case that the metal is boron, it's called a hydroboration, but in the general scheme, just a metal, then it is called a hydromethylation. And as you know from the hydroboration, this reaction generally proceeds exclusively, stereoselectively, as a Syn addition reaction. This becomes more evident when you apply the hydromethylation reaction at an alkyne. Then you can easily notice that you have a reaction as a Syn type addition process. So for the metal in this case, as we said, it works with boron hydrides, but also with aluminum as metal, sometimes with silicon, germanium, tin, and zirconium. Strongly related to this hydromethylation reactions are of course carbomethylation reactions. Well, these carbomethylation reactions will become important next semester with catalytic organometallics, especially with palladium chemistry, where this occurs very, very often. One example I would like to present, that is, as an example, the synthesis of Tamoxifen this compound is used in chemotherapy for the treatment of breast cancer. And here we have some reactions that are interesting with regards to organometallics. So, in the first step, this is the substrate, diphenylacetylene. Its common name is toluene. And it's treated with ethyl lithium in THF at minus 10 degrees. It's an addition process of ethyl lithium to that triple bond. Well, ethyl lithium actually is not very well known for addition reactions to double and triple bonds, more as a base or addition reaction at a carbonyl group. In this case, I think it works not as a concerted syn addition process, but as a stepwise process. The ethyl anion attacks, and we have this situation where this vinyl anion is stabilized through conjugation with a phenyl group. Okay? And then there is this trans equilibrium, and this one with the phenyl groups in a trans situation is of course sterically less hindered and should be favored. In the next step, this is treated with tris isopropoxyborone. And the crude product, or not the crude product, the reaction mixture, then acidified and hydrolyzed. And what we get out of this step then is this type of boronic acid. So, what did we achieve here? This is a nice example for a trans methylation from lithium to boron. These substrates became important in the so-called Suzuki coupling reaction. This is a palladium catalyzed process. What we need then is a palladium 0 catalyst, and well, for instance, an aryl or vinyl halide as the second coupling component. This type of processes we will discuss next semester in detail. So, and we got a coupling connection, a CC bond formation of this carbon with that. Well, just briefly how that works. Palladium 0 is undergoing an oxidative addition into the carbon iodide bond. We have an aryl palladium halide. The next step you can, in principle, understand as a transmethylation of this position. The boron is transmethylated with the palladium, and then you have a vinyl group and an aryl group sitting at the palladium, and in the coordination sphere of the palladium the CC bond is formed, while the palladium 2 changes its oxidation state to palladium 0. This is then a reductive elimination. The palladium 0 is formed again as the active catalyst, and we have the CC bond. giving rise to this final product. 73% for the Suzuki coupling step, and well, from the starting material to this boron compound we have 52% yield reported. Back to this general scheme, and let's discuss this halogen metal exchange reaction, the central reaction of that scheme, in detail. So, this reaction, getting from an alkyl, aryl or vinyl halide to the organometallic compounds. As we said, this is halogen metal exchange, and as a reagent we could use either the metal itself. In this case, it's called the direct synthesis of an organometallic species from a halide. While actually the term direct synthesis should, I think, also used if you take a CH acidic compound and treat it with a metal, hydrogen evolves and you have a methylated product. This should also be called a direct synthesis, I think. Yeah. Well, but this type of direct synthesis you can then characterize as a reductive replacement. Secondly, B, you could use another organometallic reagent with which you treat the halide. So, and this type of reaction is sometimes called permutational interconversion. I must admit that this term is not used very often. Sounds a bit too complicated. Details of the permutational interconversion we will discuss next week. For today we will concentrate on the direct synthesis. So, 4A. Magnesium, lithium, zinc, sometimes sodium is used. So, and the most renowned is applying magnesium, or the Grignard reagent formation. Simple example just to remember again. Bromomethane, you have clearly a delta plus at the carbon and the delta minus at the bromine because of a difference in electronegativity. treating it with magnesium in an ether solvent. You get the Grignard reagent as a Lewis acid. It is generally stabilized by two coordinated ether molecules, and you have a delta minus at this carbon, a delta plus at the magnesium, and again delta minus at the bromide. Well, and the charge has turned into the opposite at that carbon. Therefore, the reactivity has turned into the opposite, and this is called an Umpolung of reactivity. Every one of you has already done such a reaction, the production of a Grignard reagent. We know that from our undergraduate lab. And what was very important in this reaction was activating the metal. So we should talk about activation of metals. Why is this necessary? Well, because generally the surface of the metal is passivated. And the surface is passivated by an oxide layer. So, the oxide layer simply hinders the substrate, for instance the alkyl halide, to get to the surface. Somehow you should get rid of that layer. There are several possibilities how to do that. The first one is the chemically etching. In case of a Grignard reagent, in case of activating magnesium, you offer highly reactive reagents that are reactive enough to attack the oxide layer, hopefully to find a position that is still reactive enough for the electron exchange to that and thus broadening that area that is reactive enough. So indeed it starts at certain position, and the position where the magnesium is then active becomes bigger through the preceding reaction. So, most common one is simply iodide. How do you perform that? You put the magnesium into your reaction flask, add a bit of iodine, a few crystals, and then under an inert atmosphere you dry the flask again by applying a heat gun. That's it. And then the iodide goes into the gas phase and reacts from the gas phase onto the surface of the magnesium. Afterwards, you add your solvent. And if you are unlucky and it didn't work, then it doesn't start if you add then your aryl halide or the other reagent, well, you might completely be unlucky very often if the THF of the ether is not dry enough. But however, you can still try another aggressive reagent in that case, and this is the 1,2-dibromoethane. Here you also form, so alkyl halides are generally more reactive on the magnesium surface than aryl halides. So, and here you form a Grignard reagent, but this is of course short, has a short lifetime. As soon as the Grignard reagent is formed, this one, it will eliminate forming magnesium bromide and ethane, and you shouldn't worry about ethane in your reaction mixture. So secondly, you could try to activate your metal mechanically. Increasing the surface of a metal. One doctoral student of mine from Russia had a very simple method in activating lithium. He took some lithium, put it into aluminum foil, and took a hammer, flattened it. This increases the surface very well. Okay, but there are also other methods for doing that. In case of magnesium, well, how to get a magnesium powder? Well, I tried it myself with mortar and a pistol. Well, in my case, it didn't work. I know a publication, they claimed that they have, well, pistol and mortar under an atmosphere, under inert atmosphere, of course. Otherwise, it wouldn't make sense. You would get the passivating oxygen layer immediately. Well, in a publication in a Journal of Organic Chemistry about 15 years ago, a research group claimed that stirring magnesium with a simple stir bar overnight on an inert atmosphere will produce a powder. So, but they didn't give a picture of the kind of stir bar they used. I tried it with a simply one with a Teflon layer. This doesn't work at all. However, it should be possible, but I'm not convinced from the easy methods that are claimed in literature. What works very well in my own research group, that is sonication. For the sonication, this is the irradiation with ultrasound. You can use a simple ultrasonic cleaning bath, which is in every normal lab, I think. But if you need more power, you could also use a special device, a special ultrasonic device. This is called an Immersion Horn. As an alternative. So, how does this work? Well, generally it is assumed that ultrasound generates tiny little but very, very hot gas bubbles in the solution. They are very short-lived and they collapse. And if they collapse close to the surface with an oxide layer, then they bite holes into that layer. This process is called cavitation. So essentially it is, in that case, a cleaning of the metal surface. However, what is interesting is that there are also some other effects connected with ultrasound. And I found a nice example. If you treat this substrate with lithium at elevated temperature, well, again, in some kind of ether, maybe already THF, well, this CH group, this methylene group here, has an increased acidity. Well, actually, I'm wondering that it is that acidic, but we can find an explanation. It is in benzylic position, it is in allylic position, and further on you have a carbonyl group here, which on the other hand would stabilize an anionic charge through conjugation, and moreover it will stabilize the organolithium compound by intramolecular coordination. From two equivalents of that reaction, one equivalent of H2 hydrogen should be formed. So this is coordinated lithium, and you have here essentially an allylic anion with a nucleophilic center here and there. And if this center gets in close proximity to that one, CC bond formation could take place. Giving rise to this product. What is that? This is the lithium alcoholate of an NO acetal. Hydrolyzation. Forms the ketone, which is, of course, not stable, just isomerizes, tautomerizes. To the alpha naphthol as the aromatic isomer. Let's change reaction conditions. Again, lithium. And if you put that on the reaction arrow, you symbolize with this graphic abbreviation that sonication is used. You get to a totally different outcome of the reaction. This one. Very surprising. Now we can think about what happened here. Well, clearly it is an 5-exotric cyclization. 5-exotric cyclization, very often connected with radical processes, radical cyclization reactions. And the right idea is that this is a radical transformation involving radicals. Indeed, sonochemistry is regarded to promote SET processes, single electron transfer processes. So, let's see, how could we explain this reaction deriving from an SET process? One electron is transferred of course to the most electrophilic functional group, that amide. So what kind of radical do we have here? A radical anion with a lithium cation. This is some kind of, if it would derive from a ketone, it would be a ketyl radical. Okay. So again, it's stabilized here, and this radical center then intramolecular reacts under ring forming to the 5-membered ring. So 5-exotric cyclization according to Baldwin rules. You have this radical. Well, now we need to get a hydrogen to this position. Well, maybe there is another electron put on that lithium there, so an anion. But on the other hand, presumably we have an ether as a solvent. And well, such a radical would just grab a radical hydrogen from, for instance, diethyl ether, since this radical is stabilized, more stabilized as that, of course. And here the reaction might go on. So, from here to there, well, it's just a hydrolyzation during workup. So, by switching the reaction conditions to sonication, we have changed the outcome of the reaction and this is known as sonochemical switching. Also a nice expression, I think. So, next method for activating metals is solubilizing, in brackets, of metals. So actually you don't really solubilize the metal in the solvent, but well, the metal reacts within the solvent with some additional reagent. The metal disappears and the whole solution has an immense reducing quality, as if you would have solubilized metals. Yeah? Well, at least there is a general rule that says chemically solubilized is better than mechanically dispersed. Well, one example of solubilizing a metal you have also done in our undergraduate lab, the Birch reduction. Solubilizing sodium in ammonia. Okay, this is also solubilizing in brackets. So naphthalene plus sodium in THF forms a deeply colored solution. You get sodium naphthalate, where the sodium is where the naphthalene is transformed to a radical anion. The electron is in an located in an anti-bonding pi orbital, and solutions of that in THF behave indeed like solubilized sodium. Well, okay. For instance, this improves the Wurtz coupling. I think you know the Wurtz coupling, a very old reaction from the 19th century. You treat alkyl halides directly with sodium as metal, and you form then C bonds. But here in this case you have it in solution. For instance, allyl bromide plus sodium, and now just catalytic amounts of naphthalene. And you get at least an improved yield of the CC coupling product. And sodium bromide, of course. Similar activations are also known with lithium. In this case, normally biphenyl derivatives are applied. R is either hydrogen or tertiary butyl plus lithium, also mainly in THF. And again, you form the radical anion. And can apply that as a strongly reducing solution. Next method for activating is forming small metal particles. Antrazine with already somewhat activated magnesium in THF forms this interesting compound, and you can isolate that. But if you treat it again in a solution while heating it up, then, well, as you see, it is in equilibrium. Then magnesium is formed, and it's a magnesium with a high surface, a highly activated magnesium. The bigger the surface, the more active, the more reactive it is. And this highly activated magnesium or highly activated metals are very often marked with such a star. That is the mark for high activation. It has a surface of about 120 square meters per gram. And indeed it does undergo reactions which don't work with normal magnesium powder. For instance, aryl fluorides, which do not react normally under moderate conditions with magnesium, start to react at least at room temperature, forming the magnesium fluoride. And aryl bromides of course react much better than the aryl fluorides, but what is remarkable that this reaction also takes place at already minus 78 degrees and is finished within 2 to 3 minutes. So more about metal particles. You can also reduce metal salts in solution. Most of the time THF is a solvent. If you treat magnesium chloride with potassium in THF, then you get highly activated magnesium and potassium chloride. This highly activated magnesium is then called weak magnesium, because Rieke is the one who invented this type of entry to highly activated metals. They are all then called Rieke metals. However, there are enough reasons to be very, very careful with potassium. Potassium is dangerous, no doubt about that. And if you can change the method to other reducing agents, you should do so. And what you can use is, well, the sodium naphthalide. We have discussed somewhat earlier there, or also that lithium-based method, or, well, sometimes you just can use complex hydrides, lithium aluminum hydride, for instance, to reduce the salts in THF solution. So, and these Rieke metals are produced for instance, zinc, titanium, copper, iron, cobalt, and so on. Next one is similar, as you will see. It's about metal graphite laminates. This method is always connected with the name of Alois Fürstner. Developed in the late 1980s. Alois Fürstner is now director at the Max Planck Institute in Mülheim, as you might know. So, it always starts with potassium and graphite. So the stoichiometry is 1 potassium to 8 carbon atoms in form of graphite. You put the graphite in a dry flask under inert atmosphere, put in then right amount of potassium, and then you heat it up. You need about 150 degrees, 15 minutes, and you get a compound with the formula C8K. It is a bronze colored powder, of course highly pyrophoric. If air comes, if it comes in contact with air, it will start burning. So, and this is the potassium graphite laminate. But if you handle it under inert atmosphere, no problem. So, what do you do with that? You put on THF, for instance, dry THF. It's important, of course. Yeah. So, and afterwards you add the metal salt you want to solubilize, or maybe even better, you add a solution, a metal salt solution in THF into this flask. What will happen? Well, what do we have here? This laminate, you have the graphite, and the potassium went into the graphite layers and transfers its electrons. So it is some kind of intercalation of the potassium in the graphite layers. You can understand that as a form of, well, a polymeric form of what we have seen with the naphthalene. Okay? Essentially, that is the same. So, and what will happen if you add then the metal salt? Again, electron transfer processes. The metal salt will be reduced on the graphite or the laminate surface. At the end, you will have small metal particles sitting on the graphite surface. Okay? So, next step is N times C8K plus the metal salt, THF, reflux. You have highly activated metal on graphite, and somewhere the potassium halide. So the question is, what might be the advantage compared to the weaker metals? You will notice that advantage if you form weaker metals and wait some hours or days before you will apply the weaker metals. The small particles as weaker metals can move within your reaction flask, and if they get together, they will glue together. Okay, they form aggregates. This process is called sintering. So, Fürstner's method avoids sintering because the small metal particles are sitting on the surface and they just don't move, so they don't get together. An example for a nice reaction that was performed with this, based on metal graphite laminates. If you add titanium trichloride or titanium tetrachloride to the potassium graphite laminate, then you will get titanium 0 particles on the surface. And as you know, titanium is, for instance, highly reactive in the McMurray reaction. So, the McMurray reaction somehow the opposite of the ozonolysis. Double bond is formed, and this reaction with a highly activated titanium is was done even at minus 80 degrees. Another even very interesting example for a McMurray reaction is also from the group of Fürstner. Fürstner tried the following substrate for a McMurray reaction. Generally, McMurray reaction combines two identical carbonyl compounds. Of course, you don't get a mixed McMurray reaction done, except intramolecularly. So here we have aldehyde functionality and carboxylic acid amide. Well, what he tried to achieve is a new type of formation of the indole ring system by a McMurray reaction. So, first attempt was normal titanium 0 that somehow was produced, and a 0% yield was the result. Then, second attempt was titanium chloride, titanium 3 chloride plus zinc, and this is substrate A. Secondly, after the formation of the reduced titanium species in solution, the substrate A was added, and again 0% yield. Then, with Fürstner's highly active titanium on graphite, it worked very well with a 90% yield. But he found an even better method. First, titanium 3 chloride mixed with substrate A, and then secondly adding zinc as the reducing agent, resulting in a 98% yield. This, I think, is a very clever approach, and he called it an instant McMurray. So, how could we explain that? Substrate A plus titanium chloride will give a complex, because titanium chloride, Lewis acidic, it will coordinate to the best Lewis base Well, it's the oxygen of a carboxylic amide. So, the titanium chloride coordinated here. A nice idea now is we have one titanium for each substrate molecule. And the titanium is sitting there and waiting until a reducing agent comes along, or that complex approaches, in this case, the zinc surface. And an electron is transferred, not one electron, a couple of electrons, until we have the right oxidation state for the titanium already sitting at the right position for the McMurray reaction. And as you know, the first step in the McMurray reaction is the same one as we know from the pinacol coupling. Pinacol with magnesium, and magnesium then of course has the oxidation state +2. Titanium can be oxidized until the oxidation state +4, and we can eliminate titanium dioxide. So that's the reason why with titanium we get the McMurray reaction, and with magnesium it stays at the oxidation state, systematic oxidation state of pinacol, a 1,2 diol. So the best method for activating a metal is having a single atom in the right oxidation state. Therefore, we should think about further method. How do we get single metal atoms for our reaction? They should be far more reactive than small metal particles, of course. And there is one general method, not applied that often because it is a bit tricky to set that up. How do you get metal atoms? Well, you have to get the metal atoms in the gas phase first, and in the gas phase you have single metal atoms, so you have to evaporize metals. For some interesting metals you need, of course, very high temperatures. This is the problem. Yeah. So okay, and you perform such a reaction in a transformed rotatory evaporator. So imagine the following setup, which I try to draw here. So here we have a solvent, and there is a cooling bath, at about minus 80 to minus 100 degrees. Rotatory evaporator means this should rotate. Then you have a vacuum here. And you have, well, some kind of heating device in here, electrical heating device, which of course should not rotate. So you have your metal in here. It is heated up, well, to the temperature which you need to vaporize the metal. This is rotating, and you have that cooled solvent then surrounding your heating device and rotating. Metal atoms evolve here and will go into solution. That's it. Of course, it's problematic to set that up, yeah? Because if air comes into it, you have solvent here, hot metal, might cause some problems, of course. Okay? So, one very famous example and the best method to produce a certain sandwich complex is this one. You need chromium 0. And in that case you need about 2500 degrees. And as the solvent here you could use benzene. And this will form a chromium sandwich complex rather nicely. So this is certainly the high end of metal activation. In next lesson, next week, we will then discuss in more detail, well, where is it written? Well, it was this permutational interconversion. That is the next subject of this lecture. Thanks for listening. See you next week.